Hello everyone, I'm Dimitris and today I will talk to you about writing solid C++ code and a bit on why it is important. The reason for making this video is that despite a lot of great resources and videos on the solid principles, I could not find anything that uses C++ for its examples. Naturally, there isn't any fundamental difference in the solid principles themselves when writing in C++. However, as a C++ developer, when you hear people preaching about a certain way of working and you do not find any examples you can directly relate to, then you may feel reluctant and, let's say, disconnected. I personally find the solid principles not only compatible with, but also directly or indirectly promoted by the latest C++ core guidelines. Therefore, the goal of this video is to show you that the solid principles are not only relevant to C++, but also very beneficial for software targeting specialized domains such as embedded systems. Before moving on to concrete C++ examples on how to write and refactor C++ according to the solid principles, let's briefly talk about the principles themselves. As I mentioned before, there are a lot of great resources on Solid, so I will not expand on these too much. They are freely available, so go do your research. Here I will just quote the Wikipedia introduction on the topic, which I find good enough. Solid is an acronym for 5 design principles intended to make software designs more understandable, flexible, and maintainable. They are a subset of many principles promoted by Robert C. Martin. Though they apply to any object-oriented design, the solid principles can form a core philosophy for agile development. So, if you work agile, then these are some principles you better start looking into. Now, let's check out the solid principles. How this whole tutorial will work is that I will be first running a short introduction and then showing code that does not comply with each principle. Finally, I will offer some suggestions on how to refactor it. The examples will not necessarily be textbook cases because I often don't find them very easy to relate to. Instead, I will show you examples inspired by real projects which will hopefully be closer to what you may encounter. First off, the single responsibility principle. As the name implies, it requires each module, each software entity, let's say a class, to have responsibility over one and only one purpose. To put it differently, the class should only have one reason to change. When we say reason, we can, for example, mean the change in the specification of a requirement. This principle enables you to write software with high cohesion and robustness that is not going to be influenced as much while the rest of your system evolves. Let's look at some examples. Here is the photo uploader class. As we can see, it depends on 2 resources, a camera and a cloud provider. The dependencies by themselves, combined with its name, which merely implies that it uploads photos, should make you suspicious. If we move towards the member functions, we can see that the class clearly has more than one responsibilities. It takes pictures and resizes images, which depending on the context you may count as 2 purposes already, and uploads images. The problem with this class is that as soon as we have a change in the way we upload stuff to the internet, the size of the image or the way we use the camera, then this class needs to be refactored. This is a relatively straightforward example. But let's see one with a slightly more subtle violation of the single responsibility principle. Unfortunately, violations of the single responsibility principle are not always going to be so straightforward. Let's have a look at this class. We have the user manager, which depends on some kind of database. It can create users and fetch the user's report. Now, one could argue that creating a report may be counted as an additional purpose, but let's be nice and say that this is considered as part of the same responsibility. My first objection would be the inclusion of the SQL query into a higher level class. I would argue that the database schema should not be something that modules except the database should be concerned with. But in any case, let's assume that the database class in this context is a very thin wrapper. The biggest issue I see with the user manager class is that it's responsible for the formatting of the username when importing and exporting it from the database. This effectively means the user manager class becomes responsible for two things: input and output from the database based on a certain schema, formatting strings that get stored in the database. The problem with this is that if we get any requirement change in the database schema or the way we are supposed to store names in it, we will have to refactor this class. Additionally, if we want to reuse the user manager for a different product, we will either be forced to use the same schema and username format or rewrite the class. My solution to this would be to split things up in classes that have a single purpose. First, we get the database manager abstract class or interface. It offers the capability to add and retrieve users. Its concrete implementations most likely will be using the database itself and be responsible for the SQL queries and the project-specific schemas. Second, I would have the username formatter interface. This abstract class would encapsulate the different project-specific ways of formatting the usernames. This would leave us with a user manager class. The user manager class would depend on the database manager and username formatter interfaces, and therefore would be only responsible for handling the high-level user and report creation. This would allow the user manager class to be reused across projects and also be indifferent to changes in the schema and the format of the database contents. Next up, the open-closed principle. The open-closed principle is an interesting one, mainly because it has evolved through time along with programming languages. The open-closed principle dictates that the software modules are open for extension but closed for modification. This allows new functionality to be added without changing existing source code. In practice, the best way to achieve this in C++ is with polymorphism. Particularly with the use of abstract interfaces, we can extend the class and specialize its behavior without changing the interface specification. This principle allows for reusable and maintainable software. Let's look at a counterexample, something you should not do. In this snippet, we have a distance sensor class that, depending on the way we have initialized it, it effectively represents a different sensor. Unfortunately, its design does not allow us to extend the behavior unless we change the code. For example, if we want to add a new sensor model, we would have to change the distance sensor class to accommodate the new functionality. By defining and implementing an interface, we avoid having to modify that switch statement in a way that can make things quickly very inconvenient for us. As a matter of fact, we won't even need that switch statement. We start by defining what we want a distance sensor to do in general. Remember, a distance sensor is something generic. It does not have a model, therefore it does not make any sense to have a concrete instance of it. Therefore, we define distance sensor as a pure abstract class, or as we say in other languages such as Java, an interface. Then we create specializations of the interface for each of the different distance sensor models that we need. Every time we want to add a new sensor, we can create a new child class that implements the distance sensor interface without changing any existing code. We move on with the Liskov substitution principle. This principle dictates that the subclass should not only satisfy the syntactic expectations, but also the behavioral ones of its parents. To see things from a different perspective, as a user of a class, I should be able to utilize any of its children that may be passed to me without caring which child in particular I am using. This means we have to ensure that the arguments as well as the return values of the children are consistent among each other, but also with the parent. Let's see in practice why we must be able to switch or substitute among any of the parent's children without altering the behavior specified by the parent, or in particular the interface. Here we have an inertial measurement unit, the IMU. The IMU is something generic, but specifies a behavior for every class that specializes it. Particularly, it provides its users with the ability to get the sensor's orientation. The problem begins when different sensors, that is, different children that implement the interface, return orientation in different ranges. For example, we may have a gyroscope that returns an orientation that is always positive between 0 and 360 degrees. On the other hand, we may have an accelerometer providing input that can be negative, something between minus 180 and positive 180. If we had a class that should be able to use any IMU sensor, that class would read results that should be interpreted differently depending on the underlying sensor. Naturally, this would cause problems if not somehow addressed. Architecturally, having a class that is supposed to work with any kind of sensor but actually needs to know what kind of sensor it is a definite smell. Don't do that. In practice, you will see the violation of this principle manifesting itself either as bugs or calls to methods that reveal information about the child specializing the interface. For example, you could have a getIMU model function in the abstract interface. That would be bad. Don't do that. As we previously mentioned, the child classes have to be behaviorally consistent, not just in their return values, but also in the arguments they receive. Here we have an example where we must supply a frequency to a child of the inertial measurement unit interfaces. However, different children receive arguments in different ranges. If an invalid argument is supplied, the children may throw an exception, return an error value, or even worse, behave in an undefined manner, since the actual hardware sensor would not be able to make sense of the information we sent to it. There are two ways to solve this. The first one is to ensure that all children behave consistently. We should be able to substitute any of the children and the classes that use them to still be correct, to keep being valid. If this is absolutely not possible, we should think whether it makes sense to have the particular class hierarchy. We should ask ourselves, does that interface make sense? Must we really enforce this particular child-parent relationship? as a last resort, we may try to expose just enough information about the child as possible. Let's have a look at an example. In the updated IMU interface, we have included a getFrequencyRange function that returns the acceptable frequency range. This way, we can determine the valid range of an argument before supplying it to a child. I don't really like this solution, so it would personally be my very last resort, but it's at least a way to avoid bugs. Overall, I find well-defined interfaces that decouple the application logic from the domain as the cornerstone of complying to this principle. In other words, you should choose your abstractions carefully so that all children behave in a similar manner. Moving on, time to talk about the interface segregation principle. Now, this principle is rather straightforward and advocates for the creation of small and atomic interfaces. Specifically, it is better to have many single-purpose interfaces than a single multi-purpose one. This enables our software to be more reusable and customizable, since we don't have to rely or implement functionality we don't really use. Let's check out some examples. Here is a possible specification of an interface that represents a hardware abstraction layer for an imaginary microcontroller. The problem is that this interface will get progressively larger as we want to access different features of the hardware layer. The larger the interface gets, the less maintainable and reusable it becomes. For example, more work will be required if we wanted to port it to a different system. To make things worse, having to implement a large interface means that you may have to implement things you don't have any use of. What a waste of time! A very classic indication that the interface segregation principle is violated are child classes with functions that have an empty implementation. The functions are merely there to satisfy the interface and have no other purpose. Let's have a look at another more subtle violation of the interface segregation principle. Let's assume the interface of Serial Manager. It exposes functionality to send, receive, and subscribe on keys sent via serial. Then we have a MySerialManager concrete implementation that exposes the said functionality. The thing is that users of the Serial Manager interface just want to communicate over serial and don't really care about reading the stream directly. I mean, that's why we have the MySerialManager class for. How we want these users to operate is that they subscribe on certain keys and then they wait for their callback to be invoked. Additionally, they may opt to send something too. The problem with exposing the read line function via the Serial Manager interface to its users is that the interface now relays an ambiguous intent to its users. Specifically, we have given the users two possible ways to do things, but in reality, both us and them only want to use one. To comply with the interface segregation principle, we can break down the old Serial Manager interface into two separate ones. A serial client interface that exposes the functionality a typical client would need. This is to subscribe to keys over UART. This is the interface that the other modules will most likely want to use. Then we have the serial reader interface that only includes the read line function. If someone really needs to read from serial, they can use that interface, they can consume it, they can depend on it. Here you should know that the implementation of the MySerialManager class does not change. It remained exactly the same. The only difference is that it now implements two interfaces instead of a single one. Last but absolutely not least, we have the dependency inversion principle. This is one of my favorite principles and goes hand in hand with the inversion of control design patterns. The dependency inversion principle requires two things. High-level modules should not depend on low-level modules, but both should depend on abstractions. Number two, abstractions should not depend on details. Instead, details should depend on abstractions. What does this practically mean though? In traditional layered architectural styles, the higher level components which implement the system's application logic depend on lower level components that contain the so-called domain logic. Let's have a look at a simplified example inspired from embedded Linux use cases. We are building middleware that receives signals from the UI and, depending on the business rules, sends messages over serial to some external hardware. The components that decide what should happen depending on the received messages are the high-level ones, while the ones that are responsible for the communication with the UI and the serial port are the lower-level ones. In a layered architecture, the business or application logic components should be using the communication components. Here we have the decision maker, which uses or depends on the user interface communicator and the serial interface communicator classes. The problem is that our application logic is tightly coupled with the domain logic. To put it differently, even if our decision maker operates depending on independent business rules, it will not be reusable in different settings such as different products. That is, unless we use exactly the same implementation for the user interface and the microcontroller that we may want our Linux system to talk to. So how do we fix this? This is a problem. We don't want our new products to be forced to use the same code and the same hardware. And also we don't want to keep changing software that we don't really need to. We abstract the essence of the lower level components in interfaces, and we make our higher level component depend on the specific interfaces instead of the implementation. Now we can migrate our decision maker to different hardware as long as the interface to talk with the UI and the serial port remains the same. This effectively allows us to create new products or new iterations of the same product without having to excessively rewrite unrelated software. We can respond to changes in their environment or in customer needs quickly in an agile manner. Now that we covered the theory, let's have a look at some code. We need to schedule the upload of some files to the cloud, let's say AWS, and therefore we create the file uploader class. The AWS Cloud class handles uploading to the S3 bucket, where the term S3 bucket is specific to Amazon Cloud Services. By looking at this, I see two potential violations of the dependency inversion principle. Number one, our higher level component depends on some lower level functionality. This is fine. Unfortunately, we do not depend on an interface, which means that we are coupled to a very specific implementation. This means that if we at some point decide to move to a different cloud provider, we will need to re-implement the file uploader class, which contains logic that should be pretty much independent. Why should the file uploader care about whether we use Azure, AWS, or Google? It just wants to schedule uploads. Now let's see the second violation. Let's assume that we have refactored things and created the cloud interface. The cloud interface now exposes the upload to S3 bucket function, which does the uploading, and file uploader now depends on it. This is still problematic. We have an abstraction, the cloud interface, that depends on a detail, specifically the fact that an S3 bucket is being used. This means that if we were to start using another cloud provider, we would have to either add yet another function named after the other provider, thus complicating everything and violating other solid rules, or use a name that is not accurate. Of course, both of these are bad, therefore, it is not enough to just take the header file of a concrete class and create an abstract interface out of it. We need to carefully think what is the essence or the capabilities we want to offer and name the functions as well as the abstraction itself appropriately. We need to design things and name things and decide signatures without leaking or imposing implementation details. Let's see how our solution should look like. We have maintained the cloud interface. However, we have used a generalized name for the function that handles the upload. Now there is nothing that implies that a specific cloud provider should be used. All the cloud interface needs, or children of the cloud interface need, in order to upload something is a file path and nothing more than that. This way, we have managed to both get reusable software and avoid vendor lock-in, or at least in a software level. Now that you have some examples on how to apply the solid principles in C++, I hope you will go forward and design or refactor your systems to be as agile as you claim your company processes to be. I am sure you will not regret it. If you think that what you heard is not applicable to you due to domain constraints or because you use a language that is not object-oriented, such as C, you should know that this may not be entirely true. From talking and watching some pioneers in the embedded industry, the essence of solid principles is totally applicable when using C as your primary language and are writing software for, let's say, a real-time operating system. It's mainly the semantics that change. So I do encourage you to look more into this yourselves. That was about it, folks. I hope I did not make you tired. Please don't forget to like, subscribe, and share this video to promote better software and help me create more videos. Take care.